Hello everyone, my name is Arya Gupta and I will be giving a presentation on the paper Extending Lattice Linearity for Self-Stabilizing Algorithms. In this presentation, first of all, we will introduce the problems that we have addressed in this paper. We will give an example algorithm. We will discuss how that algorithm possesses the property of lattice linearity and what are the benefits behind such an extension. Finally, we will conclude the presentation. We are going to study the minimal vertex cover problem in this example graph, which contains two nodes connected to each other by an edge. Rules for node 1 are as follows. If both the nodes are in the vertex cover, then node 1 changes its state to out. And if both the nodes are out, then node 1 changes its state to in. Rules for node 2 are same as the rules for node 1. Let's study what happens when algorithm 1 is applied and both the nodes perform execution at the same time. Let's study state 3. Now node 1 reads that both the nodes are in and therefore node 1 can change its state to out. Node 2 reads the same, and as a result, both the nodes turn themselves out of the vertex cover, and the next state is global state 4. When we are at state 4 and both the nodes read the states of each other at the same time, both the nodes will turn themselves in, and as a result, the next state will be global state 3. In such cases, it may so happen that we obtain an infinite sequence of states, with state 3 and state 4 being present at alternating positions, and the graph may never reach an optimal state. So algorithm 1 may converge with interleaving executions, centralized scheduler, or with the usage of locks. But it may not converge with a scheduler which may select more than one nodes to perform executions simultaneously. Let's generalize algorithm 1 for general graphs. We have two macros. A node I is removable if and only if every edge that contains I shall be covered even if I changes its state to out. And a node I is unsatisfied if and only if there is at least one edge which contains I and is not covered. Algorithm 2 is the generalization of algorithm 1, where if a node I is removable, then I changes its state to out, and if a node is unsatisfied, then it changes its state to in. Now, how do we fix this problem? What we want to do is we want to move to a feasible state as soon as possible, and therefore we want to allow state 4 to transition to states 1, 2, or 3. But we don't want to violate the feasibility once we are in a feasible state, and therefore we don't want to move from state 3 to state 4. So we have to put some restrictions here. The restrictions that we have put is we are only allowing node 2 to move out if we are in state 3, and therefore state 3 cannot transition to state 4 or state 2. It can only transition to state 1. What we have done here is we have declared node 2 to be the forbidden node because node 2 is of a higher ID, and therefore state 3 can transition to state 1 only. Let's generalize the notion of a node being forbidden. Only if a node is forbidden, we want to allow it to change its state to out. There are three conditions. I should be in the vertex cover, I should be removable, and for every node j adjacent to I, j should not be removable, and even if j is removable, then the ID of j should be less than the ID of I. Our algorithm is put as algorithm 3, where if a node I is forbidden, then I changes its state to out, and if a node I is unsatisfied, then I changes its state to in. So if we apply algorithm 3 on any of these states, we are guaranteeing convergence because state 3 only transforms to state 1. This slide gives a little hint about application of lattice linearity to algorithms. What we have done here is we have deemed node 2 to be the forbidden node. Node 1 has to wait for node 2 and allow node 2 to change its state to out first. Only after node 2 changes its state to out, node 1 can reevaluate its cards and decide if it is forbidden. Because of this, even if nodes are reading old values, algorithm 3 is guaranteed to converge. Lattice linearity has been studied earlier by Vijay Garg. In that paper, the task was to find a predicate which represents a problem as a lattice of states. There can be many feasible states, but only one optimal state. and the algorithm is required to start from a specific initial state. This slide depicts our motivation behind extending lattice linearity to self-stabilizing algorithms. If we allow state 3 to transition to state 2, we are allowing node 1 to be forbidden. If we allow state 3 to transition to state 1, we are allowing node 2 to be forbidden. But in state 3, both the nodes cannot be forbidden. And even if we allow both the nodes to be forbidden, state 3 can be allowed to transition to state 4. But we don't want that to happen. In fact, minimal vertex cover problem is not a lattice linear problem. It does not possess a lattice linear predicate. There can be more than one optimal states possible for general graphs. Our algorithm is divided into two phases. In the first phase, we move aggressively towards a feasible state. As we enter a feasible state, the algorithm starts to behave lattice linearly, and only the forbidden nodes are allowed to leave the vertex cover. We call such algorithms eventually lattice linear self-stabilizing algorithms. Benefits of such algorithms are listed in this slide. We don't have to require nodes to run in lockstep. Nodes can perform execution without any requirement of synchronization. We can allow nodes to perform execution in read-write model, and we can allow nodes to rely on old data, and still algorithm 3 is guaranteed to converge. We have extended such algorithms to other problems and designed algorithms for those problems. These problems include with the graph coloring problem, maximal independent set problem, and the service demand based dominating set problem. Such algorithms can be transformed into fully lattice linear algorithms, where in addition to moving towards an optimal state selectively, we will move towards a feasible state selectively as well. And in that, we will give priority to nodes having lower ID. We call such algorithms lattice linear self-stabilizing algorithms. Some interesting future work directions are also listed. It might be interesting to study if we can implement approximation algorithms under the paradigms of lattice linear and eventually lattice linear self-stabilizing algorithms. It might also be interesting to study exactly what class of problems can be solved under these paradigms. This concludes my presentation. Thank you.